Ready?
Let's do it.
Yeah. Okay, we'll start the next session. But first talk is by Aaron Sidford from Stanford, talking about methods for computing stationary distribution.
Thank you very much for the introduction, and thank you very much for organizing this workshop. Today I'm going to be talking about faster algorithms and new iterative methods for computing the stationary distribution. This talk is based on the following two papers, which are on arXiv. And this talk is a reflection of a sort of long-term project we've had with a number of wonderful researchers at MIT and Georgia Tech. And everything I'll be discussing in this talk is the byproduct of this rather concerted effort all of us have made to try to get faster algorithms for the problems I mentioned in this talk, computing the stationary distribution, simulating random walks, and getting new primitives for processing Markov chains. So everything I'll say in this talk is joint work with Michael Cohen, Jonathan Kellner, John Peebles, Richard Pang, Adrian Vladu, and Anoop Rao. But before I go on, I just wanted to take a moment, talk a little bit about Michael Cohen. Michael Cohen was a graduate student at MIT and a fellow here at the Institute. He was an amazing collaborator, a huge force on this project, a rather big influence in the theoretical computer science community, and by pretty much the account of anyone I've ever talked to, a rising star in the field. As many of you know, sadly he passed away in the last 2 weeks. And I don't think I can even begin to do justice with, I think, the incredible impact he's had on the community and like the amazing, impressive style with which he did research. And how nice it was to work with him. But I did want to at least take a moment to say that everything I'm going to say in this talk, Michael very much had his hands in it, and nothing I want to say in this talk I think would be quite what it is if it wasn't for Michael's outstanding contributions to this project. And moreover, even the way I think about it, or the way I'm going to describe everything, is very much the product of my interactions with him. And from everyone I've talked to, this is not unique to me. It was hard to have a short conversation with him and not be left with a changed view of whatever it was you started with thinking of. And I think the fact that he was a major contribution to at least 3 of the talks this week, it was rather representative of his work. And I think in the years to come, we're still going to be, for a long while, I think, be seeing the ripple effects of his outstanding work and style to research. So I just wanted to take a moment for that. He'll be missed. All right, so without further ado, I guess the main thing I'll be talking about in the rest of this talk is a problem you're all familiar with, you've all seen in some way, shape, and form. The problem is as follows. We are going to assume for the rest of the talk we have some large directed graph. We'll assume throughout this talk that this graph is strongly connected. And what we're going to do is consider probably one of the most natural random processes you could consider on this graph. We'll consider the standard natural random walk on this graph. So we'll consider the process where we're at some vertex. We pick an outgoing edge from this vertex with probability proportional to its weight. We go to the vertex that the edge points to, and we repeat. Pick an outgoing edge proportional to weight, follow it, and repeat. And the question we're going to ask in this talk is how fast can we compute the distribution that this process converges to if it converges to anything? In other words, how fast can we compute the stationary distribution? So a little notation, another way to see this, throughout the talk I'll use the matrix W to denote the random walk matrix associated with the graph. Every column of W is indexed by a vertex of the graph, and the column simply corresponds to the distribution over vertices that result from taking one step of the random walk from that vertex. So the goal in much of the rest of the talk is to compute the distribution over vertices S, such that if I pick a vertex from this distribution and take one step of the random walk, I get back the distribution. Or in other words, to compute the vector S, such that if I look at the random walk matrix times S, I get back S. So that's the main problem we're going to consider throughout the talk. All right, so why would you want to solve this problem? It's a rather fundamental problem. It's one of the first properties of random walks and Markov chains you might consider. Computing this more or less corresponds to computing things like personalized PageRank. And moreover, computing this is related to computing a lot of other natural properties of random walks you might want to compute. Things like computing commute times, or hitting times, or escape probabilities. It also shows up in some maybe slightly more surprising contexts. So I guess yesterday there was a talk on solving Markov decision processes. And if you want to solve a Markov decision process, so you have a number of states, For every state, there's some action you could possibly take that'll give you some reward and randomly transition you to another state. If you then want to compute the best policy, or if you, I guess let's say you have a particular policy, so you know for every state what action you're going to take. If you want to compute the long-term reward that you glean, if you take this policy, look at the reward you get, do the transition, and repeat. If you want to compute the average reward this gives over time, computing this is very closely related to things like computing the stationary distribution. So in the machinery we'll talk about this talk, we're also getting faster algorithms for things like evaluating the policy of a Markov decision process. Why am I talking about this result in this workshop? I guess there are two major reasons I thought it was worth talking about in this workshop, beyond maybe a personal preference that there be at least like one Laplacian system solving talk in the workshop. And the reasons are as follows. First, when I talk about, as we'll see later throughout this talk, some of the way we'll get faster algorithms for solving a variety of these problems will be by building some what I think are rather interesting iterative methods that I don't think we've quite mapped to the broader family of optimization methods we well known. So they're rather, I think, non-standard iterative methods tailored a bit to the linear algebraic structure of this problem. I think there's a chance maybe representative of some broader sort of algorithmic methods we're not having a handle on. So if you want a challenge problem to think of as I go through the rest of the talk, you can think like maybe to what degree are any of these things that we're doing maybe representative of some new iterative methods we're not using. And the other reason I thought it was a good thing to mention in this talk is that the end result of a lot of this will be some faster algorithms for processing some things in random graphs. And I have some hope that these methods could possibly be used to develop faster algorithms for further problems down the pipeline. So combinatorial problems or further things involving random walks. And as you might get a sense from seeing how we go about getting the results in this talk, I think any result that uses this thing as a primitive to solve some of these sort of combinatorial harder problems will probably have to do something, again, a little non-standard or non-traditional in the iterative methods in order to get that work. So I think there's some non-standard iterative method questions both underlying the results of this talk and how you might use the machinery the talk gives down the road. All right, so computing the stationary distribution is a fundamental, well-studied problem. I've maybe argued a little, it's not quite trivial. What I want to do, though, is before going into what's the runtimes we actually get for this, I think I want to say a little bit about why personally I'm very excited about this topic and about the work of this talk. So my personal interest in computing the stationary distribution, or why I guess myself and a lot of the rest of the group got excited about this problem, has to do with a certain revolution that's been happening in the area of algorithmic graph theory over the last decade that many of you are well familiar with, many of you are experts in. So this is known as the Laplacian paradigm. And if you haven't heard this, it refers to a relatively natural, I think, straightforward idea in the design of fast graph algorithms. So the Laplacian paradigm refers to the following. It says on the one hand, there's a class of combinatorial objects that we want to understand better, we want to get faster algorithms for. We can look at the set of undirected graphs. So these are graphs with n vertices, some m edges, and some non-negative edge weights on the edges of the graph. Now on the other hand, there's this broad class of linear algebraic objects that arise in a variety of contexts that we might want to understand better as well. And these are Laplacian matrices, which are simply symmetric matrices that have non-positive off-diagonal entries and have the property that every diagonal entry is equal to the sum of the off-diagonal entries in the corresponding row or column. All right? Now, it might be immediately obvious. It doesn't take long to see. There's a natural bijection between these combinatorial objects and these linear algebraic objects. Clearly, I can just associate whether or not there's an edge between I and j in the undirected graph with whether or not there is a negative entry in entry ij of the matrix. And I can associate the weight of the graph with the weight of the edge in the graph with the magnitude of the off-diagonal entry in the matrix. So we have this natural bijection between these two objects. And through this natural bijection, it's been a long, well-studied area of research that you can try to go between linear algebraic properties of the matrix to get better understanding of combinatorial properties of the graph. And this is through an area that's known as spectral graph theory. What the Laplacian paradigm refers to is the fact that a little over a decade ago, there was a breakthrough result of Spielman and Tang, 2004. This is a widely inferential, very powerful result that showed actually we can solve linear systems in Laplacian matrices in nearly linear time. So an incredibly well-studied problem. The set of now faster algorithms we have and improvements and consequences for it are more than I can list in this small part of the page. But for what the Laplacian paradigm refers to is beyond the impressive research in solving Laplacian systems in nearly linear time. Given the connections of spectral graph theory between Laplacian matrices and undirected graphs, we can use the fact that we have this new primitive for extracting linear algebraic properties from these matrices, namely we can solve linear systems of them, to better extract combinatorial properties of undirected graphs. And that's what the Laplacian paradigm refers to. So this has been an incredibly successful algorithmic paradigm, and for a long list of problems you might consider, the fastest algorithms now use in some way, shape, or form our ability to solve Laplacian systems in near linear time. So solving Laplacian systems directly corresponds to things like modeling electric networks and simulating undirected random walks and computing page on undirected graphs. There's a number of numerical applications. For example, Madhuri's talk earlier in the week on matrix scaling was using the ability to solve Laplacian systems. The ability to solve Laplacian systems. And there's been a growing list of combinatorial applications, so things like computing partitionings of undirected graphs, solving maximum flow in certain regimes approximately on undirected graphs, sampling random spanning trees, and it's been a rapidly growing list of problems. All right. So this begs a natural question. What about directed graphs? What can we say through this paradigm about our ability to get faster algorithms for solving directed graphs? And here there are some very exciting results. There have been some real breakthroughs on our running time for solving directed graphs. But in some sense, the running time improvements that have been gleaned are a bit more mild. And the running time improvements I know of from using Laplacian system solvers or the algorithmic machinery that underlies them to solve directed graph problems essentially boil down into two main camps I can think of. The first has to do with you can view the ability to solve Laplacian systems as the ability to simulate certain simulate networks of resistors and compute where electric current flows. You can also view it as the ability to compute minimum norm projections onto the space of circulations of a graph. And when you have that latter primitive, then it's not too hard to see that if you can solve Laplacian systems, you can implement iterations of interior point methods for solving a variety of graph problems. You can implement the iterates of these interior point methods in near linear time. So doing this and using a variety of really clever, sort of impressive tricks to get to modify those interior point methods, there have been faster algorithms for directed graph problems like minimum cost flow, directed max flow, and shortest path with negative edge lengths. And there's also been some results on using the machinery that underlie getting some of the faster graph algorithms to get faster algorithms for problems on directed graphs when the directed graph is sort of Eulerian or undirected enough, when the cut metric on the directed graph looks fairly similar to an undirected graph. And that's sort of the state of things. These substantial runtime improvements, but the running times are still a bit far from linear. I think it's like m to the 10�7ths for maximum flow or shortest path with negative edge lengths. It's not quite some of the full near linear time algorithms we have for the undirected case. And this gap is for not lack of trying or lack of creativity. There are some real barriers that come up if you try to take any of the Laplacian system solving machinery and use it to solve problems on directed graphs. Namely, there's a lot of these results for getting fast algorithms on undirected graphs use our ability to compress undirected graphs. There are sparse graphs that preserve their distances. There are sparse graphs that preserve their cuts. There's ways of decomposing undirected graphs while preserving lower properties. And it's not too hard to show that a variety of these things just do not exist for directed graphs. If you haven't saw it before, the example that sort of rules out a lot of natural sort of compression things you would try to do, it's not very complicated. You simply take a bipartite graph, a directed bipartite graph. So you put some n vertices on one side of the graph, put some n vertices on the other side, and start adding edges from one side of the graph to the other. All right, that all point in the same direction. If you stare at this for a little bit, it won't be hard to convince yourself that if you can do things like preserve whether the distance between vertices, then you can check whether or not an edge exists in this bipartite graph. Or if you can multiplicatively check the size of a cut, how many edges leave a set of vertices, then you can also check whether or not an edge exists. And consequently, you need n squared bits in order to be able to compress the directed graph. And there's a variety of natural things you might do to try to get around these counterexamples, but it rears its head in some ugly ways for a lot of these things. All right, so that's sort of the issue with extending this machinery in directed graphs and sort of getting all the benefits of the Laplacian paradigm for directed graph problems. And I guess that's what brought myself and our researchers, the other researchers in this group, to the problem of computing the stationary distribution. We're looking for, can we possibly get sort of the same sort of wins from solving undirected Laplacians? Can we get the same sort of nearly linear time primitive for something undirected graphs? Like maybe there is some nearly linear time primitive that's just missing from our toolkit. And maybe if we look for the right problem, we can find some sort of comparably robust directed spectral graph theory. Maybe what we shouldn't be doing is trying to use the undirected Laplacian system solvers, and rather we should find some new primitive better tailored to directed structure where we can solve this new problem in near linear time. There was some really intriguing, or more broadly you can ask, like, what is the right way for looking for directed graph structure that's similar to the way in which we found undirected graph structure when we solve undirected Laplacian systems. There was some really intriguing work of Fan Chung on Cheeger inequality for directed graphs, and some work on directed local partitioning from Anderson, Chung, and Lang, but not still this like full sort of robust nearly linear time algorithm for extracting properties from directed graphs when the problem might be very ill-conditioned and poorly behaved. All right, so if you want to go and try to follow this program of try to find this directed comparably robust directed spectral graph theory, the first question you might ask is, well, what's the right notion then? What's the right problem? What's a good notion of solving of directed Laplacians? And the way I've rigged everything up before, there's a very natural thing you might try. If we started from saying there's a bijection between undirected graphs and symmetric matrices, that corresponds just from associating off-diagonal entries with edges of the graph, we could just do the same exact bijection between directed graphs and asymmetric matrices. We could simply drop the criterion that our undirected graph is undirected. We could drop the criterion that our Laplacian matrix is symmetric. And what we'll do is just we'll just associate every off-diagonal entry of the Laplacian with whether or not there's an edge from I to j, but not also from j to I. All right? So this is a very natural definition. It's the first thing you might try. But the first question you should ask when doing this is this actually meaningful? Is this problem actually worth study? Like, this seems very mathematically nice, but that's not an argument that it's actually useful for really extracting structure from directed graphs. However, with a little work, it's not too hard to show that if you can solve these directed Laplacian systems, then the running time you get for solving these directed Laplacian systems essentially corresponds to the running time you need for solving all of the applications I talked about in the beginning. So if you could solve directed Laplacian systems, you could compute expected commute times, escape probabilities, evaluate the policy of an MDP, and compute the stationary distribution. And so the main result I'm actually going to talk about in this talk is how to solve directed Laplacian systems faster, and therefore get faster algorithms for computing the stationary distribution and the slightly broader set of problems I talked about in the beginning. All right, yes?
I think I might be missing something. So do you have to do some transformation of like a Markov chain transition probably to turn into this Laplacian form?
So in a little bit later in the talk, we'll talk about the exact mapping from directed Laplacians to stationary distribution, and I think it'll become really clear. So yeah, if you want to compute the stationary, we'll talk more directly about computing the stationary distribution. I guess for the moment I'm saying take on faith, or as a homework assignment, that there's a mapping from directed Laplacians to stationary of Markov chains. I'll do it explicitly a little bit later in the talk. If it's not clear, let me know. That answers the intuitive part of the question?
Yeah.
Good. Yeah?
Another quick question. So since you mentioned special classes of directed Laplacians, right? Is there something corresponding to time reversible Markov chains? Is that
a little bit. We'll get there. So the key insight in all of this is will eventually be what's the right class of directed Laplacians to target, and it'll be Eulerian Laplacians, and we'll get to it shortly. Okay. Any other questions? All right, so before I talk about what we actually did for solving this problem, let's just do a quick summary of what the state of the art was, or what the fastest algorithms were for solving each of these problems, computing the stationary distribution, solving directed Laplacian systems, and all these other applications. Each of these problems is incredibly well studied. There's a variety of interesting work in theory and practice. There's much more that I could possibly cover. and way too many results for me to actually enumerate. But what I can say is, as far as I know, all the previous results for solving these problems essentially fell into one of three categories. All right. So first, there's a variety of results for solving these problems when you assume some sort of good conditioning of the problem. You can compute the stationary distribution when the random walk mixes quickly and time polynomial in the mixing time. You can compute personalized page rank when the restart probability is fairly high. You get a polynomial dependence on the restart probability. So a lot of these algorithms, there's some sort of measure of complexity of the problem that you depend on polynomially. And with that dependence, you can get a variety of interesting trade-offs and algorithms that depend polynomially on it, but maybe fairly well on the dimension or the size of the input. There's also a variety of results that solve these problems approximately. So they only compute them up to some polynomial accuracy. There's a variety of interesting, there's some sampling results in saying you can distinguish between sort of like stationary, large, or small, or things like that. So there's a variety of results on computing them to polynomial accuracy. And the other way you can naturally solve all these problems is just to use general linear system solving machinery. Solving all of these problems ultimately boil down to solving a certain n by n linear system. And you could, where the number of non-zero entries in the matrix just is the number of edges in the graph. And you could use off-the-shelf linear system solving machinery to solve them. If you used fast matrix multiplication, this would give a running time of n to the omega, where n is the number of vertices in the graph. Or if you didn't think about precision issues, which I think is something you should think about, conjugate gradient would give you a running time of mn, where again m is the number of edges in the graph, or the number of non-zeros in the matrix, and n is the number of vertices. Main way to remember this is the running times are all super quadratic or larger if the graph is sparse. Okay. So the main result I'm going to tell you about in the rest of the talk is how to solve all of these problems in almost linear time. The algorithm will have a polylogarithmic dependence on the condition number, so it'll still run fairly quickly even when random walks don't mix quickly, as long as they mix polynomially quickly. They'll all have a polylogarithmic dependence on the accuracy, so they'll all be linearly convergent algorithms. They'll have a logarithmic dependence on the accuracy you're aiming for. And ultimately, the algorithms will use more than sort of general linear system solving machinery. We'll ultimately use some graph structure to get faster algorithms for solving these problems.
That's always weird to me about these these things that are relying on Laplacians. We've seen many talks this week about taking advantage of graph structure, and somehow there's always in the theoretical computer science community, for whatever reason, it's always we have to go through SDD. Mm-hmm. And then there's like a variety of linear system direct solvers that do like chordal completions, approximate chordal completions, multifrontal Cholesky, right, which are very competitive. And actually, usually, I mean, they run in.
So I think that's a wonderful point. I'm not trying to argue. I think that the theory we're doing here is unlike anything that happens in practice, and that there's unlike any practical analog for solving these things quickly. When I talk about these previous results, I'm saying only the theoretical running times and not a lot of the amazing practical work that's happened.
Can I just make a comment on that? Yeah. Which is that one thing that's really cool about this is that applied people, when you tell them, oh, we can solve undirected Laplacians in nearly linear time, they say, yeah, so can we. But when you tell them we can solve directed Laplacians in nearly linear time, they're like, what? We do GMRES for that, like conjugate gradient descent, basically. Cool. Yeah.
Thank you. Thank you.
We use a direct solver.
Or a direct.
Thanks. That give a flavor of the answer. Okay. Any other questions? All right, so how do we do this? And a quick, in case you try to look up the papers later, we did it in a few steps. The first step is we showed, and this was exactly what you were asking about, that in order to solve all of these problems, we provided a reduction that showed it actually suffices to solve directed Laplacians in the case when the graph is Eulerian, in the case when the in degree is equal to the out degree. It's not a direct reduction. We provide an iterative method that reduces solving an arbitrary directed Laplacian to solving a sequence of Eulerian Laplacian systems, where the number of iterations you need, the overhead is just polylogarithmic in the size of everything. So that's the first step. And in the first paper, then what we showed is that these Eulerian Laplacians, when in degree equals out degree, you can actually solve. We showed first that you could solve them slightly faster than you could if using just generic linear system solving machinery. So we got the following complicated running time, which you should think is just a little bit better than n squared when your graph is sparse. Right? So this was a proof of concept. It showed that like Eulerian Laplacian systems and through this reduction directed Laplacian systems did have some non-trivial structure to exploit. However, the algorithm we did use symmetric Laplacian systems. So this was saying like, good, you can do something about understanding directed random walks, but sort of by bounding how well you can approximate them by undirected random walks in the right way. So it was a proof of concept there was structure, but not sort of tailoring anything to the directed structure of the graph. All right, so how to do better? In the second paper, we showed that you could get at this problem about whether or not directed graphs compress. And you can show, at least for the sake of preserving properties of random walks, things like commute times, things like commute times and certain properties of random walks. These you could actually compress in a directed graph. So we proved that there are directed spectral sparsifiers, meaning there are sparse directed graphs where if you want to solve a linear system in a dense directed graph, you can actually, it suffices to solve it in a sparse one. So you can preserve enough of the structure of the graph. And then we showed that given the ability to sparsify directed graphs, showing that they do compress in some reasonable way, we then showed you could go through the sort of a lot of the amazing work that's happened in the past on solving undirected Laplacian systems and then tailor it to this directed setting to get an almost linear time algorithm. So what am I going to do in the rest of the talk? I want to tell you mainly about these, the first and the last results. So I'm going to tell you how to reduce solving Eulerian Laplacians, solving arbitrary directed Laplacians to solving Eulerian Laplacians, which is a sort of interesting iterative method that I alluded to in the beginning. And the rest I'll talk really briefly about how you then actually solve Eulerian Laplacians. So how you get spectral sparsifiers and through that build an iterative method for solving them in near linear time, almost linear time. So that's the plan for the rest of the talk. Any questions before I dive into directed versus Eulerian Laplacians? All right, so first question we should ask, why do we actually want to reduce to solving Eulerian Laplacian systems? The short answer is working with directed Laplacians in general are rather degenerate. So if all we have is a directed Laplacian, meaning we have this matrix where the off-diagonals are non-positive, and every diagonal entry equals to the sum of the absolute value of the off-diagonal entries in the corresponding column, then for such matrices, even if the corresponding graph is strongly connected, there's a real issue in solving them that we don't even know their kernel. So we can't really characterize when there even should be a solution. And if you're going to try to solve this system by sort of approximating it by some other system or doing something recursive, this is sort of like the base sanity check you should have, that you at least understand the kernel of the matrix. And why don't we understand the kernel of directed Laplacians? This is getting to the question you asked me earlier. It's very related to the problems we talked about in the beginning. So a directed Laplacian we can always write as the diagonal matrix corresponding to the out degrees of the graph minus the adjacency matrix of the graph transpose. Okay? That just gives the mapping of the off-diagonal entries in the diagonal, which means if you multiply the Laplacian by D inverse and D, that means we can write the directed Laplacian as the identity matrix minus the random walk matrix, this again, which we talked about in the beginning, where every column is a distribution over the vertices you get from one step of the random walk from a vertex. And the Laplacian is just the identity minus the random walk matrix scaled by the diagonal out degree matrix. However, as we discussed in the beginning, we know from Frobenius, we know that there's some unique vector, when the graph is strongly connected, there's some unique vector S, the stationary distribution, such that W times S equals S. And therefore, this means that if we look at D inverse times S, this is in the kernel of the directed Laplacian, because we'll get the D inverses cancel, and we'll have I minus W times S, which is S minus S is 0. All right? So it says the kernel of a directed Laplacian is given by essentially the stationary distribution. Right? So if you could characterize the kernel of a directed Laplacian, you could characterize the stationary distribution of the corresponding random walk matrix. All right? So even the problem of just getting the kernel of this matrix is the problem of computing the stationary, which as we argued is roughly as hard as all the other problems we said. However, Eulerian graphs are much nicer. If the graph was Eulerian, if the in degree was equal to the out degree, then it's not too hard to see that just the degrees are the stationary distribution. And the all ones vector then would be in the kernel of the Laplacian. Right? So if the graph was Eulerian, we know its kernel very well. It's just the all ones vector. Yeah?
Assuming that the weights W's are 1?
No, their weights are arbitrary.
So when
not negative.
D is diagonal.
When I say every time I say degree, I mean weighted degree.
Okay.
I mean the sum of the weights leaving an edge. Yes, great question. But yeah, weighted in parentheses every time I say degree. That answers. Okay. All right. So this says why Eulerian Laplacians are possibly nicer. We at least don't have this issue of not knowing their stationary distribution. However, that doesn't say why we can always hope to reduce to solving Eulerian Laplacians. However, this isn't quite too hard to see. As we've just argued, we have a directed Laplacian. If we look at the random walk matrix, we argued that the stationary distribution of this random walk matrix times the degree is its kernel. And the claim is if you let the matrix X denote the diagonal matrix, whose every entry is this vector in the kernel of the directed Laplacian, it's not too hard to see that if you just simply multiply the directed Laplacian by X, what this means is you take every vertex in your graph and you scale the outgoing edges by this vector, by the coordinate for that vertex, the xi. Then the resulting matrix is Eulerian. All right? So I'll call this vector x the Eulerian scaling of the Laplacian. So it says if you can compute the stationary distribution, you just reweight all the outgoing vertices and you get an Eulerian graph. Seeing this is not hard, but just to introduce a bit some notation we'll use in a second. This is connected to a certain quick algebraic way of checking if something is a directed Laplacian. So we said a directed Laplacian has non-positive off-diagonal entries, and that every diagonal entry was equal to the sum of the off-diagonal entries in the corresponding column. Since the off-diagonal entries are all negative, this is the same as saying the all ones vector is in the left kernel of the directed Laplacian. Okay? So I'm going to say this directed Laplacian has non-positive off-diagonal entries and tight column diagonally dominance, meaning, again, the diagonal entries are the sum of the absolute values of the off. Now, a matrix is Eulerian if and only if when I look at the all ones vectors in the right kernel, because that would give that the out degree is also equal to the sum of the incoming weight, which I'll say is saying that's tight row diagonally dominance, that every diagonal entry is equal to the sum of the absolute values of the corresponding row. So what that means is if we take a directed Laplacian and we scale it by x, clearly I'm not changing it by the left kernel. I'm also clearly not changing the sign of any entry. And we chose x exactly so that when I multiply it by the all ones vector, it's in the kernel. So that means if we had the stationary distribution, we multiply it by the out degrees, and then scaled our Laplacian accordingly, we'd get an Eulerian Laplacian. All right? So what this says is if we knew the stationary distribution of a directed Laplacian, we could simply scale and use an Eulerian Laplacian system solver to solve it. All right? So this reduces everything to this new problem of how do we actually compute the stationary distribution, assuming we could solve Eulerian Laplacian systems. If we could do that, we'd then be done because we just use our Eulerian Laplacian system to compute the stationary, scale it, and then solve the linear system with the Eulerian Laplacian system solver. All right, so how do we actually do this? So again, our problem is we have this directed Laplacian, and we want to get this non-negative vector x, such that if we look at L times x, it's both row and column diagonally dominant, meaning which I'm going to denote RCDD, meaning every row is larger than the absolute values of the corresponding row, and every column diagonal entry is larger than the absolute values in the corresponding column. Now the way we're going to compute this is a rather natural, I think kind of natural iterative method that'll try to improve the proximity of our matrix to being row column diagonally dominant. So the rough idea of the iterative method we'll do is just as follows. We'll start with some bad guess of the scaling, some bad guess of how to scale every one of the vertices in the hopes of making row column diagonally dominant. It won't work. It won't be row column diagonally dominant. So we'll simply add a bunch of stuff to the diagonal to make it row column diagonally dominant. All right? And then what we'll do, so when we add a bunch of stuff to the diagonal, this will make some excesses in some of the rows and some of the columns. Like things won't be tight. They'll be a little larger than they should be. And we'll then subtract something from the off-diagonal entries that's natural to turn the thing into a Laplacian. Okay? And what we'll do is we'll use the fact that this Laplacian we created came very simply from a row column diagonally dominant matrix, and use that if you can solve Eulerian Laplacians, you can solve row column diagonally dominant matrices, and then therefore you can characterize the kernel of this matrix that came directly from it. So we'll use that. So what we'll do is then compute the stationary of this Laplacian using an Eulerian solver, use this as the new scaling, and iterate, hopefully showing that our matrix gets closer and closer to being Eulerian. All right, so that's the rough idea. The algorithm looks like is the following. We start with, we have some initial excess scaling vector x. This is our guess of the scaling that makes it Eulerian. And this excess vector e, that's how much we have to add to the diagonal to make it row column diagonally dominant. So we'll maintain that E plus L, this diagonal matrix plus our Laplacian scaled by x, is row column diagonally dominant. What we'll then do is turn this into a Laplacian. And it's not too hard to see that if you simply do this rank 1 update of this row column diagonally dominant matrix, you get a Laplacian. This matrix just has a little more in the diagonal than it should. So if you simply pick these two vectors to have the appropriate row norms, you can make it so that the all ones vector is in the left and the right kernel. Right? So we get this Laplacian that's just a rank 1 update of our row column diagonally dominant matrix. What we'll then do is try to compute the stationary distribution of this Laplacian. All right? So there's a pretty easy reduction to say that you can solve, all right, saying that if you can solve linear systems in Eulerian graphs, there's a standard reduction that was done also for symmetric matrices, saying you can solve the case when the diagonal, rather than having strict diagonally dominance, you have true diagonally dominance, like the diagonal is larger than the absolute values in the corresponding row or column. So what we'll use is that we can solve Laplacian systems in E plus L if we could solve row column diagonally dominant systems, because these are just a scaling away from a row column diagonally dominant system. We'll then use that reduction I said to say we can solve E plus L using an Eulerian Laplacian system. And then what we'll use is that the kernel, since L prime is just a rank 1 update of a system we can solve, turns out you can just directly and that you can show that E plus L is actually invertible. Means you can directly characterize the kernel that results from doing this rank 1 update. So it's simply a single linear system solve in E plus L that'll give you the kernel of this new Laplacian. All right? So that's what we'll do. We'll solve one Laplacian system to get the new scaling. To get the scaling of this Laplacian, we'll use that as our new scaling. And then what we'll do is we'll update the excess vector accordingly to be the smallest thing we can such that it's row column diagonally dominant. And we'll repeat. Now, if you stare at this for a little bit, it's not too hard to see that this algorithm actually always makes progress. If you really solve the linear system exactly, no matter sort of how you pick G, this algorithm will always decrease the excess vector, like the amount you had to add to the diagonal to make it row column diagonally dominant. And the reason is when we go from here to here, we're subtracting this rank 1 update. This was some mass on the off diagonals that was possibly hurting row column diagonally dominance. So how much we remove always gives us progress on the excess. So every iteration of this, E is monotonically decreasing, right? The amount of excess vector. So it's not hard to, wasn't too hard to figure out this algorithm, be like, this is a natural way to try to make progress. What's perhaps more surprising or not clear is how much progress it makes. But what you can show is the following. If you measure the original excess, like how much you had to add to the diagonal to make it row column diagonally dominant, this isn't too hard. You can show that it's not too large to begin with. It's something that depends only on dimension. But what you can show is in every single iteration of this algorithm, you actually decrease this measure of excess by a multiplicative constant. So every single iteration of this algorithm is actually having the amount of excess, the amount you had to add to the diagonal to make it row column diagonally dominant. So what that ultimately means is you just need to do roughly like log n over epsilon iterations of this algorithm, and you have a matrix that's very, very close to being row column diagonally dominant. So close you can just approximate it by an Eulerian Laplacian system and solve. So that's the algorithm.
So what is that OTL hiding?
So there's a few good questions. So there's a few details hiding here. You have to talk about how precisely you need to solve this to make the iterations work out. So you have to talk about the accuracy you actually need in the linear system solves. Also makes the analysis a little easier to make it truly row column diagonally dominant, to like maintain a little bit of buffer there. And all that the log is hiding is that buffer. Is hiding that buffer, and I guess there's another log hiding perhaps from the precision with which you need to solve a Laplacian system. So it's just a log n over this buffer that you're maintaining. Good question. Any other questions? All right, yeah?
Oh, so wait, so there's no condition number dependence in this part?
No. There is, I guess, in possibly in the linear system solver. But in terms of the convergence of this, you say if I just want to have something like alpha multiplicatively row column diagonally dominant, I need log n over alpha iterations, and that works. Yep. Any other questions? Okay, good question. All right, so that's all I want to say about this. Now I'm running a little short on time, so I might have to do the next part a little quicker than I might like, but I'd be happy to chat about it more. So we've just shown how you can reduce solving directed Laplacian systems to solving Eulerian Laplacian systems. Let's talk about how to solve Eulerian Laplacian systems in near linear time. So for the rest of the talk, we're going to solve the same problem. We want to solve Lx equals b, where we're also assuming that the diagonal entries are equal to the sum of the absolute values in the corresponding row. So now L is associated with a strongly connected Eulerian graph. The way we're going to solve this is the standard technique for solving linear systems. What we'll want to do is compute some matrix Z. This fairly well approximates the inverse of the Laplacian L, and then run this simple method known as precondition Richardson to get a more and more precise answer. So all we'll do is we'll keep measuring, we'll maintain some iter at xk, we'll look at how close we are from Lxk to equal to b, transform it by Z and take a step in that direction. Think if Z was exactly the inverse of L, this method would converge in one iteration. What we'll try to do is compute Z that well approximates the inverse enough that this converges fast. So our goal is to compute this preconditioner Z in almost linear time such that we can apply it in almost linear time and such that we don't need too many iterations of this method. The way we'll actually measure the quality Z is we'll simply look at how close Z times L is to being the identity matrix. So how close is Z to being the inverse of the Laplacian L? What we'll end up doing, the norm we'll use in the analysis will end up being the one associated with the undirected graph. So if I have an Eulerian Laplacian, so we'll think of our Eulerian Laplacian and think of the natural undirected Laplacian associated with it, where every forward edge we replace with a half an edge forward and half an edge back. So it's a natural undirected graph that's associated with it. And we'll use the norm induced by that to measure our progress. Now there's a real issue in trying to construct such a preconditioner Z. And the real problem in this is that sparsification, or the ability to approximate symmetric, this is the procedure that was used for solving symmetric Laplacian systems. And there's a real issue that the ability to sparsify or approximate undirected graph by a sparse undirected graph was rather critical to the construction of pretty much all preconditioners that we knew before in some way, shape, or form. And those that didn't use something like approximating distances, but still there was some sort of tight spectral approximation that had to happen here. However, neither of these things are known to exist for directed graphs. So this might seem kind of daunting, but you might also hope that perhaps we can do better here because we've assumed that our graph is Eulerian. So maybe we can use Eulerianness to get maybe for Eulerian graphs we can get around some of these issues and still construct a sparsifier. So quick recap of undirected graph sparsification. Let's see what we would want in the undirected case. So in an undirected case, a spectral sparsifier is simply as follows. You have a symmetric Laplacian U. You want a symmetric Laplacian U tilde that approximates U. The measure of approximation uses the standard spectral one, saying that their quadratic forms are multiplicatively approximated up to 1 plus minus epsilon for all x. And we want U tilde to be sparse, meaning the number of entries is proportional to the quality of approximation and the number of vertices in the graph, not the number of edges. We call U a spectral sparsifier if both of these things hold.
What is the NB?
Huh? I'm just defining what it means for spectral. Yeah, this is just a self-contained definition. Yep, good question. All right, so why do you want this in the symmetric case? It turns out if you have a spectral sparsifier for in the symmetric case, then its pseudo-inverse suffices as such a preconditioner, if you could apply it efficiently. And why is it possible to compute these sparse graphs that approximate? It basically has to do with the fact that you can write a symmetric Laplacian as a sum of symmetric Laplacians over the edges of the graph. So it decomposes edgewise. Yeah, I know. Okay, decompose over the edges of the graph. So you can subsample them and approximate the matrix. If you try to do the same thing for directed graphs, the simplest Eulerian sub-Laplacian of Laplacian is a cycle. They might all be long, so the concentration inequalities get really messed up from sampling cycles, and we don't know the right measure of approximation. Now I think I'm way over time, so I'm going to do this. I'm not way over. Oh, how much time do I have?
You're definitely over.
All right, let me do like the one sentence version of the rest. I'll be happy to talk the rest of the day. All right, so what did we show? We picked this complicated measure of approximation. It generalizes the directed measure of approximation. It implies a good preconditioner and some bunch of other cool properties like preserving commute times. The way we computed it is we went back to the way sparsifiers were first proven to exist by Spielman-Tang, showed you can adapt it to the directed case. Big barrier to overcome, or that was tricky in the analysis, was something about having to exactly preserve the degrees or preserving Eulerianness. And this was sort of the difficult thing in the analysis that eventually made it all work out. The way you use it is we essentially used a similar approach from Peng and Spielman in 2014, that there's a cool recursion for writing the inverse of a matrix by repeatedly squaring the matrix. We used that same recursion, but there were some issues to get around from the fact that error grows a bit faster in the setting that it does there. So we had to do some tricks to get around this to make it work out. That's how we solved an almost linear time. I'm hiding a lot of numerical precision issues, a whole lot of details on how to make these pieces work. Also, this would only give a 2 to the root log kappa dependence, where kappa is the condition number. So there's another trick you need to get it to log 1 over epsilon. There's also a lot of tricks to get all the reductions to the other problems to work out. I'm happy to talk about it more. But the upshot is directed graphs have structure. There's now a lot of cool problems that maybe the door is open on to use this machinery to solve. And I hope you take this to go to solve more problems I can't even think about and maybe help us create this like robust directed Laplacian paradigm. Thank you. Sorry for the time.
Okay, maybe we can take one quick question while Marcus is.
Well, not
Sorry.
Any question? Actually, I have one quick question. Eulerian graphs in MDP, what does it mean, for example?
Ooh, good question.
For what MDPs would it?
Good question. So the question was, when in an MDP do you have an Eulerian Laplacian? And I guess that seems, it's a good, I haven't thought about it. I'd take it offline, but I guess my first thought is it seems tricky to still have like non-trivial action sets that are always Eulerian, because that seems like a rather rough constraint. But I'm happy to talk about it more. That's a great question. But I guess the point is that everything is Eulerian after scaling. So it means if you want to try to use these in an algorithm, you just maybe have to reason about the Eulerian scaling along the way. Sorry, I handed you the wrong cable.
Okay, thanks.
Yeah, thanks.
Let's thank Aaron again.
No worries. No, it's okay.